In my last series of lectures, I went through the definitions of the kinematics of quantities. Velocity is the derivative of position with respect to time. Acceleration is the derivative of velocity with respect to time. You understand more and more what those definitions mean by using them. That's what we do here throughout the remainder of Chapter 2 and into Chapter 3. The simplest case to describe mathematically involving one-dimensional motion is one-dimensional motion with constant acceleration. One-dimensional motion with constant acceleration can be described algebraically. It's the only case involving motion that can be described algebraically, that is, when the acceleration is constant. For all situations involving non-constant acceleration, the only way to mathematically describe such situations is through the methods of calculus. But with constant acceleration, we can describe it algebraically. Let's say that we know three things about an object's motion. First of all, we know where the object is when we start the clock. So we know the initial position, x0. Let's say that we also know how the object is moving when we start the clock, so we know the initial velocity, v0. And then let's say that we also know how the velocity is changing with respect to time, the constant acceleration, which I'll just simply write as a. Now, as long as the acceleration is constant, the instantaneous value and the average value of the acceleration are, of course, the same number. So I'll write the acceleration as a, as opposed to writing it as a bar. Okay, now if I know these three things about the object's motion, then at any time in the future, I should be able to determine two things: where the object is as a function of time, and then how it's moving as a function of time. In other words, we need to find equations that describe the position x and the velocity v as functions of time. If I can find those equations, then I have a complete description of the motion, and we can easily find those equations by using algebra. So we need to find position and velocity v as functions of time. Okay, here's how this derivation begins. We begin with the description of average acceleration. Average acceleration is change in velocity with respect to time. Now, on the right-hand side of the expression in the numerator, recall from the kinematics definitions that the change in velocity delta v is the final value minus the initial value. The denominator of the expression we just simply write as time t. We always presume to start the clock at times t is equal to 0. Therefore, the time interval itself is just simply written as t. And now, right here is what I'm looking for, a description of the velocity as a function of time. So now we do a little bit of algebraic manipulation to simply solve for v. So let's take the time t and move it up here to the left-hand side like so. And then let's take the v0 here and move it to the other side of the expression like so. And when I do, I now have one of the equations that I'm looking for. Velocity as a function of time in terms of the initial velocity and the acceleration. So right off the bat, I have one of the equations. We'll then find the second equation by beginning with the description of average velocity. Average velocity is change in position divided by change in time. Let me begin this derivation much the same way as I did a few moments ago, previously with the other derivation. Let's go ahead now and write the numerator of the expression on the right-hand side of the expression as final minus initial position. And then the denominator will once again just simply write as t. And then right here is what I'm looking for, a description of position as a function of time. So now algebraically, let's just solve for x. So move the t here to the other side. And then move the initial position x0 to the other side to then get the position x like so. Now, there's nothing wrong with this equation, but it's not quite what I'm looking for, because it does give me position as a function of time in terms of initial position, but also instead in terms of average velocity, which is not one of the quantities that is given. So then therefore I have to do a couple of extra steps. Those couple of extra steps involve the mathematical definition of average. Whenever you find the average of a bunch of quantities, you always add up those quantities and then divide by the number of quantities that you have. Here we're talking about average velocity. So now let me write the average velocity mathematically in the following manner. Average velocity is equal to the initial plus the final, but then divided by 2, because after all, we have here 2 values of the velocity. Let me go ahead and substitute that into this expression for position. Like so. This here is a little bit closer to what I'm looking for. It's giving me position as a function of time in terms of initial position and in terms of the initial velocity, but also in terms of the final velocity v. But we already know what the final velocity v is. That's this expression here that I derived earlier. So the last couple of steps involving taking this expression now for the final velocity v and plugging it into here. Like so. This equation here now gives me what I'm looking for, a description of the position as a function of time in terms of the initial position, the initial velocity, and the acceleration. The equation itself, by the way, is cleaned up a little bit. If we add things together here and simplify in the parentheses of the expression, multiply through by this time t, you ultimately end up with the following equation. This expression here. This expression here is the same thing as the expression above, just algebraically cleaned up a little bit. Let me go ahead and summarize the 2 equations that we have here thus far. These 2 equations here are a complete description of this simple type of motion, one-dimensional motion with constant acceleration. If we know where the object is when we begin, how the object is moving when we begin, and how the velocity is changing as we begin, we can then in the future find the position and the velocity of the object at any moment in time. This is a complete description of the motion. Okay, now you were able to follow me algebraically in this series of steps to arrive at these expressions. But of course, as of yet, you really have no idea exactly what these equations are saying. You understand what these equations are saying by using them. So at this point, we'll go ahead now in part 2 of this lecture in just a few minutes to start to take a look at some examples.